In this lecture, we are going to complete the proof of local existence and uniqueness theorem for Cauchy problems for the general nonlinear equations. So, we start with a recap of what happened so far, and then we go to step 3, which namely defining a candidate solution. So, we will define a candidate solution by applying inverse function theorem, and then we show that the candidate solution is indeed solution. So, this is to recall the notations. QL stands for quasi-linear equation and GE stands for the general nonlinear equations, or sometimes people call it fully nonlinear equations. Of course, GE contains L, SL as well as QL, but when it is presented in this form it is called generally nonlinear equations. Okay, where are we in solving the Cauchy problem? The key steps involving in the solution of Cauchy problem were identified. Step 1 is to obtain a system of ODEs for the characteristic strip, and step 2 is a finding initial strip. Third one is to define a candidate solution, and fourth one is establishing that the candidate solution is indeed a solution. So, steps 1 and 2 were successfully implemented so far, and let us recall the difficulties once again which are new to GE when compared to QL, and what are the ideas that helped us to overcome them. So, our analysis was motivated by quasi-linear equations QL. So, QL gave us characteristic direction gave rise to characteristic curves made up an integral surface. Now, equation GE does not give away a characteristic direction. So, a usual idea, we observed that for quasi-linear equations the characteristic direction is the envelope of possible tangent planes. In fact, the possible tangent planes envelope is a straight line which has the characteristic direction. So, we found that the same idea works for GE as well. So, characteristic direction at a point p x y z is given by Fp Fq P of p plus Q of q. The argument has to be 5 tuple p p q. Capital P stands for x y z, small p and small q, they are such that capital F of this is 0. And characteristic ODE system is incomplete for general nonlinear equation, because when we try to find a curve which has a characteristic direction, it has to satisfy this set of ODEs, namely chara ODE, but here P and Q appear which themselves are unknown. So, this is not solvable, and we need to add equations or supplement the system with another 2 equations, one for P and one for Q. It has been achieved, and that was called chara strip ODE, where the dP by dt, dQ by dt equations have been added. Now, next question is that can we pass characteristic curves through points of the datum curve? This is what we did in QL. So, for that we need to solve chara strip ODE with initial conditions given by points of the datum curve. Initial conditions for x, y, z are given by the datum curve. No initial conditions are known for P and Q. So, they were found in step 2, which was called finding an initial strip. Next step is to solve the initial value problem, chara strip ODE plus an initial strip, that will give you a candidate solution. It will define a candidate solution, we are going to see that. So, from now onwards what we assume, maybe in deriving these equations we have assumed a certain higher smoothness conditions on FGH and the capital F or maybe U, but do not worry, now onwards we assume this, that characteristic strip ODE is given, equations are given to you, you do not have to derive, and initial strip consisting of C1 functions is found. Of course, we cannot find perhaps throughout gamma, but you look at a point Fs0, Gs0, Hs0 on gamma, and hence I want this to be defined nearby that point P0. and let these functions x, y, z, p, q, which are functions of t and s, solve the IVP. What is IVP? Characteristic ODE supplemented with this initial conditions coming from initial strip. Now, defining a candidate solution, this is where we need to apply inverse function theorem to certain functions and then get a candidate solution. So, we are interested in the invertibility of this function. What is this function? This is actually the base characteristic curves, right. The trace is base characteristic curve as t varies, passing through the point FSGS, which is on gamma 2. So, near this point 0 S naught, which belongs to j cross I. So, now to apply inverse function theorem, the Jacobian is required to be non-zero. Of course, we need to check whether phi is C1, that is C1 because x and y are solving ODEs, therefore, the derivative with respect to t is continuous, no problem. With respect to x, it is also differentiable and C1 because of the differentiable dependence. So, we have the C1s of phi. Now, we need that the Jacobian is non-zero. The Jacobian is this. As before, we do not once again analyze with g of Ts because nothing is known for a non-zero t. So, only at 0 it is known. J of 0 S naught, the Jacobian is this, which is f p f q at the point zeta naught and f dash s naught g dash s naught. Of course, the way we got P s and Q s is such that P of s naught is P naught, Q of s naught is Q naught. So, you could as well write here P s naught, Q s naught, but remember we started with P 0, Q 0, a particular solution of the system of equations which defined P s and Q s later on. So, you can write P s naught, Q s naught or P naught, Q naught because both are actually the same. Now, the Jacobian condition is precisely the transversality condition. Okay. F prime g prime corresponds to what? Tangent to gamma 2, tangent to the gamma 2. What is gamma 2? Projection of gamma to xy coordinate x omega 2. This is the tangent. This is the base characteristics, tangent to the base characteristics of this direction Fp and Fq. We have to assume this is non-zero, that means they are not parallel. So, base characteristics cut gamma 2, that is the transversality condition. This is same as the delta naught that we saw in the step 2. So, defining a candidate solution by inverse function theorem, there exists an open subset E of j cross I containing the point 0 comma s naught and F, which is an open set of omega 2 which contains x of 0 s naught, y of 0 s naught, which is actually f s naught g s naught, and a continuously differentiable function from F to E such that these two compositions are identity maps on respective spaces. This is a picture which depicts. So, this is the phi map we went. Inverse function theorem told that there are neighborhoods E and F and a map psi is defined. This is where we are using Ts coordinates, here we are using xy notation. Phi restricted to E is a diffeomorphism and so on. And denotes psi of xy equal to T of xy S of xy, and the equation psi circle phi is identity on E, phi circle psi is identity on F. They give T equal to Txy, S equal to Sxy. So, recall that ZTS was expected to be the value of the solution at the point XTS YTS. Therefore, this motivates us to define a candidate solution by using this Z. So, U defined on F to R U of xy equal to Z of Txy S of xy. As a function U is a composition of two C1 functions, by chain rule U itself is C1 function on F. So, step 3 is successfully completed. We have defined a C1 function as a candidate solution. In the next step we are going to check that this is indeed a solution. So, this is a solution to the Cauchy problem if the following identity holds for every xy in F, that is capital F of xy, uxy, uxxy, uyxy equal to 0, and the Cauchy condition u of fsgs equal to hs is satisfied. So, define I dash to be those values of s in I for which fsgs belongs to f. Okay. So, this is that I dash which came there. So, s belongs to I dash, we will be the datum curve will be on the corresponding integral surface defined by this u. So, observe that T of fsgs is 0 and s of fsgs is s. Thus, for s in I dash we have u of fsgs equal to, by definition of u of fsgs, u of any two quantities is T of fsgs comma s of fsgs, but that is nothing but z of 0 comma s, which by the definition of z is h of s. Therefore, Cauchy condition is satisfied, that means a piece of the datum curve lies on the integral surface corresponding defined by this function u. Now, we have to still check that u solves the PDE. So, proving that for every xy u satisfies the PDE, namely f of xy, uxy, uxxy, uyxy equal to 0 holds is the same as showing that for every Ts in E, f of xts, yts, zts, ux of xts, yts, uy of xts, yts is 0. Okay. Because xy and ts are in 1-to-1 correspondence via diffeomorphism. Therefore, showing this is same as showing this. And we already know that for Ts in J cross I, f of xts, yts, zts, pts, qts is 0. Okay. This we have seen in step 2 while defining initial strip, we did that. So, this is known, we want to show this. There is a difference between the two, the difference being in the last two coordinates, ux xts yts is here, pts is here, uy xts yts is here, qts is here. Suppose we show that this pair of functions of ts is same as this pair, then we have shown this because it is already known. So, let us try to do that. Let us show that pts is ux xts yts, qts is uy xts yts. So, this is the triple star is what we want to show. Then this holds, okay. This we already observed on the last slide. That completes the proof. So, what remains to show is these two equalities. How are we going to show that? We prove that this pair is this pair are same by showing what? We will show that this pair is a solution to a system of non-homogeneous linear equations. This is also a solution of non-homogeneous linear equations. The same system has a unique solution because the coefficient matrix there will be invertible. Therefore, the solution must be the same. We know that the system Ax equal to b, if you have Ax1 equal to b and you also know that Ax2 is equal to b, that would imply x1 equal to x2 if you know that A is invertible. Okay. Solution is unique. So, we are going to show this, we are going to derive this system of linear equations which both the pairs satisfy, and we will show that the coefficient matrix is invertible. Therefore, the solution is unique. Therefore, if you knew Ax1 equal to b and Ax2 equal to b, then it must be that x1 should be equal to x2, and then it will follow that this pair is same as this pair, which is triple star. So, now we have to get those system. How do we get that system? So, differentiating this equation zts equal to u of xts yts with respect to s and t will give us two equations. For convenience, I write in the matrix form. Okay, what is zs? Zs, that is the first equation. Zs means ux into xs, that is you see ux into xs plus uy into ys. So, ys into uy. So, that is the first equation. This one is this into this. Okay, this is a matrix, this is a vector, this is a vector. So, this equation is very clear. Now, we claim, so what is this equation? This is satisfied by ux xts yts, uy xts yts. This matrix acting on that will be zsts ztts. Now, we are going to show pts qts also satisfy same system. See, the coefficient matrix is same, in this case I have written as the left hand side. So, this is same, this is same, and if this is invertible, these two must be same. Is this invertible? That is the question. It is invertible because change of variables. Change of variables, this is a Jacobian corresponding to change of variables. Therefore, this will be always invertible. So, therefore, the moment we establish this system, it automatically follows that this pair is same as this pair. Now, how do I derive this 5 actually stands for this equation. How do I derive this is missing in the LaTeX compilation, it has vanished. Okay. The second equation follows from characteristic ODE because that is what it is, right. Zt equal to xtp plus ytq. What is xt and yt? They are fp and fq. So, it is p of p plus q of q. Therefore, this follows. So, we have to show the first equation. The first equation is this, we want to show. So, we want to show that this thing equal to 0, let us call it by ATS. We want to show that ATS is 0 for every TS in E. How are we going to show this? Because this features derivatives with respect to S, that may be the difficulty. Okay. For each S we show as a function of t, it solves an initial value problem at plus fza equal to 0, a of 0 s equal to 0. Okay. We will show that it solves this initial value problem. Now, by uniqueness of solutions to initial value problem, ATS must be 0 for all t. Why? Because this initial value problem will have only 0. 0 solution is a solution. A of t equal to 0 is a solution. Here it satisfies this condition. Therefore, if this is a linear equation, if this is continuous coefficients, this will be Lipschitz. Therefore, you have a unique solution. Therefore, ATS will be 0 for every t, and this happens for every fixed s. Therefore, ATS is 0 for all Ts. Fine. So, we have to derive this equation, that is all remains to show. A of 0 s is 0. Okay. All s. This is coming from the definition of initial strip, H prime equal to P f prime plus Qg prime. Okay, differentiating ATS, we have to derive an equation satisfied by ATS. So, the only thing you can do is differentiation. So, AT equal to ZST, right, PT XS, QT YS, P XST, Q YST. Now, a small rearrangement is required, it is an algebra. So that we will get Fz into A minus Fz into A. So, we are going to use Cara strip ODE equations here, and we end up getting this, that is same as minus Fza because this is 0. So, we use that dou by dou s of f is 0, which is a consequence of f of xyz pq being 0. So, note that the coefficient matrix appearing in the system of equations 4 and 5 is the same, we already observed. Its determinant is precisely this. It is the Jacobian corresponding to the change of coordinates x, y and Ts. Therefore, it is always non-zero. Thus, the linear system 4 5 has a unique solution. Thus, we have proved the following local existence and uniqueness theorem. Uniqueness proof proceeds as in the case of quasi-linear case. So, I am not going to do it here. So, what is the theorem? Assumptions on f, omega 5 is an open set, connectedness is not required, open set. let f be a C2 function that we cannot dispense with. Fp and Fq satisfy that both of them cannot vanish simultaneously at any point of omega 5. Assumptions on Cauchy data, Fgh are C1 functions, so no need of C2 functions, just C1. And assumption on initial strip and transversality condition. So, assume that this system Fs, Gs, Hs, Ps, Qs equal 0, Ps f dash plus Q g dash equal h dash admits a solution Ps Qs, where Ps Qs are continuously differential functions on the interval I. Actually, we have it is enough to work with existence of these kind of functions for S in a small interval containing some point S0. Because finally, the conclusion of inverse function theorem or implicit function theorem are local. So, assume the transversality condition. Conclusions are the general nonlinear PDE admits a solution defined in an open subset of omega 2 for the Cauchy problem, that is missing here, Cauchy problem. The Cauchy problem for general nonlinear PDE admits a solution defined an open set of omega 2, which is f actually. It is not d, it is actually f. We have found d is equal to f. The proof in the proof we have d is equal to f. And the point Fs naught Gs naught is in f satisfies UFS Gs equal to Hs for those S for which this is in f. Further, the solution is locally unique. So, let us solve an example of where we are going to solve a Cauchy problem for a nonlinear equation, the simplest nonlinear equation ux square plus uy square equal to 1. Cauchy data is given by u is 0 on the circle, x square plus y square equal to 1. So, first thing as always is to parameterize the Cauchy data, x equal to cos s, y equal to sin s, z equal to 0, s in the interval 0 to pi. System of ODEs. So, what is f of x y z p q? P square plus q square minus 1. So, in this example, so we should always write this, what is this function? From here we can compute very easily fx, fy, fz are 0, fp is 2p, fq is 2q. So, dx by dt is fp, therefore 2p, dy by dt is fq, therefore 2q, dz by dt is pfp plus qfq. What is pfp plus qfq? Let us write down once maybe. fp is 2p, fq is 2q, pfp plus qfq is equal to 2p square plus 2q square. But the equation says p square plus q square equal to 1, therefore, this is 2. And dp by dt is 0, dq by dt is 0 because our f does not involve x, y, z at all. So, we have to now complete into an initial strip the datum curve. We have to find Ps Qs satisfying two conditions. One is the equation Ps square plus Qs square equal to 1. Second is Pf prime plus Qg prime equal to h prime, that will give us this. Now, we have to find solutions. Here we see clearly two solutions. Of course, you may say infinitely many solutions because you can mix both of them, because this is an algebraic or whatever transcendental equation, right. At some s you can be here, at some other s you can be here, you can keep on oscillating, but that is not good. What we need is a smooth function. This is very important, because what we are trying to solve, just recall, whether quasi-linear or fully nonlinear, we take gamma, we take a point on this and we pass a characteristic curve through that and repeat for everything, right. Whenever you choose a point on gamma, it will correspond to some s, and then you are simply passing a characteristic curve through that. Another s dash you take, you pass another characteristic curve. Why should these characteristic curves together stitch or weave a surface? That would happen if things underlying are smooth functions. that is why FGH we assume C1 functions. So, here we need to assume PS, QS also smooth functions, otherwise we do not expect. So, that is why there are two choices for smooth functions. So, P1S, Q1S is cos S sin S, other one is minus cos S minus sin S. So, smooth is very important. So, there are only two if you insist on smoothness. Now, if you take the initial strip where PQ is taken to be cos S and sin S, the solution of Kara strip ODE will be this. I am not going to the computation because it is a very simple ODEs that you can solve. So, these are the solutions XTS, YTS, ZTS, PTS, QTS. Now, from the first three equations we get this relation x square plus y square equal to z plus 1 whole square, and ZTS is given by this formula. On simplification you get that. So, we define a pair of functions u1 and u2, one with plus sign, one with minus sign. Then the solution to Cauchy problem is given by this and not the minus 1. Why? It does not satisfy the Cauchy data, you can check that. So, if we proceeded by taking the initial strip as minus cos S and minus sin S, then we would have got this as a solution and not this. This will not satisfy the Cauchy data, this will satisfy. So, summary is for this lecture is that the candidate solution was defined, we verified that it is indeed a solution to the Cauchy problem. A closer look at the proof of existence and uniqueness theorem reveals proofs of the existence and uniqueness theorem for both QL and GE are strikingly similar, actually the same, but for obvious modifications. Once characteristic tips have been obtained, because we need that XTS, YTS, ZTS, right, and we always work with XTS, YTS to get inversion, right. Inverse function theorem is applied only for XTS, YTS, whether it is QL or GE, and the extension of ideas were clearly brought out in our presentation. So, this completes the analysis of Cauchy problem for general nonlinear equations. In the forthcoming lectures, we take up some problems based on this. Thank you.